Okay, so you won't believe it, but last week on Monday in Pierce, I was down in the basement. I never go to Pierce, and I'm never going back again because I left my stuff alone for like 5 minutes, and somebody stole my computer and my phone out of my backpack, which means like I got it back, and then less than a week later, it got stolen again. And then it got turned on. Find My iPhone continues to be unhelpful, so I continue to encourage you not to use it. It turned on once, and it was in MIT like 15 minutes later, and the person called this phone number that showed up in my AT&T call log. So I went online, called that phone number, and it went straight to this answering machine in Spanish. And so I haven't heard of it since. So I had to get a new computer and phone. I know. Yeah. But if you guys want to chip into my computer fund after this, that's why I've asked you here. Just kidding. Wow. But, yeah, that was really sad and traumatic. But it's all back now. And that was why the PSET 8 took so long, because I didn't have a computer. And somebody stole it. And I emailed asking if they would grade your PSET 8, but they said no. And I was like, can I have my computer back? And they're like, no. Just kidding. Okay, this is our final section. And I have a couple of, we only have 3 things on the agenda. We're going to talk a bit about the Q Guide, then we're going to spend 15 minutes on a cool demo, then we're going to all say goodbye to one another. You don't really need your computers or a pen and paper to take notes or follow along. So I assume if you have your computer open, you're on Facebook. Just saying. Unless you're filling out the Q Guide, which is first. The Q Guide is open. You've had an email about it. I get, once all the Q stuff is submitted at the end of the year, I get all of the Q comments and scores from everybody who chooses to give me feedback. And so when you go in the queue, I don't know if you can do this, Jeff, because you're an extension student, but when you go in the queue, if you haven't done it before, you pick your teacher, which is David Malin. You have to do him, and then you can pick TFs, and you can pick as many TFs as you want. But there are 60 of us, so you don't have to pick everybody. You can just pick me, or just pick like a couple other people if you want to give them feedback as well. And then you get scores on all these different axes, and then you can leave them feedback. And then like a month later, I'll get all that feedback. And just like the feedback you've been giving me throughout the semester, I read all of that, and it's really helpful, and it helps me grow as a teacher and as an individual. So please take some time to do it. We're only going to be here for like 30 minutes. So if you want at the end of this to like take 5 minutes and just fill out the queue, because it doesn't take any more time than that, that would be wonderful. And you also get your grades back more quickly if you fill out the queue. So most of you have done that before, or no, about half of you have done that before. But if you're a freshman, that's what that is. It'll be the same for all the classes. Do it. It takes 5 minutes. But also, if you do it a bit seriously, that's not the worst thing in the world, because I certainly take it seriously. So if you leave me like a smiley face, I will appreciate that. But I would also appreciate if you left me more than a smiley face. But it's up to you. I can't tell you what to, or like a big smiley face with like a capital D. That would be even better. Okay, that's all I have for the queue. If you have any questions, you can ask me, but pretty self-explanatory. Just please fill it out. I would really appreciate it, and it means a lot to me. Okay, this is what we're going to spend 15 minutes going through. I'm going to show you some code. I think this is really cool, and this got me more excited in computer science, so I hope it will do the same for you all. We are going to open up, and all this code I'll send to you later. But we're just going to open up. I'm in my terminal. We're going to open up this program called MySum. And can everybody read that, or should I make it bigger? Sweet. It is cool. Okay. Can anybody tell me what this code will do when I run it? Or what this program will do when I run it? Avi, what do you think it's going to do? Finish chewing. Shouldn't talk with your mouth open. Okay.
Does it take a bunch of arguments, find the sum of them, return the sum, and then print it out? Or it takes in 2 arguments, and then it does funky with skirt tall, and then it prints out whatever the result is?
Close, really close. Anybody want to add to what Avi said? Do you need to give this program any command line arguments? No. What happens if you don't give it any command line arguments? I just write /mysum. 1 plus 2 equals 3, and it'll print that out. That's exactly right. You see that printf line at the bottom. It'll print out A, B, and then the sum of A and B. And you're assuming, I guess you assume that sum works correctly. Good assumption. Okay. And what happens if I give it one argument? Madhu?
It'll add whatever the first argument is to be, or to 2, sorry.
Right, to 2. Does anybody know what strtol does? It's basically A to I. A to I is actually a fancy version of, or a simpler version of strtol, but it actually uses strtol. And I found that out because I wanted something like A to I, and then when I did A to I read down here, and I found this behavior is the same as strtl. So it's basically A to I for all intents and purposes. And you see I even use null and 10. This actually lets you take a string and turn it into a number and choose what base you want to do it in. So this is base 10 right here. I could have done base 2 for decimal, base 16 for hexadecimal. It's pretty cool. But long story short, this takes 2 numbers and adds them together. So let's run it. And you'll also notice there are some things. So I have a make file right here. And if you open that up, some things you'll notice are different. In particular, this argument right here. You probably haven't seen that before. Generally, we compile things with -00. -00 means don't do any optimizations, compiler. Do everything. Don't try and make anything fancy or make anything run more quickly or get rid of variables that are unnecessary. Don't optimize this code at all. I'm asking for third-level optimization. So I'm asking the compiler to do a lot of optimizations. You can change that in the make file when you have this code if you want to see different stuff, which we'll show in a second. So we run mysum 1 plus 2 equals 3. Somebody give me 2 arguments. 4 and 5. Thank you. Great, it works. What are some other good arguments to try to make sure this works? Anyone? 0. And it works. But those were good choices. Okay, so let's go back here. This is mysum.c. You'll notice there's also something called sumfunction.c, and this says, oh, there's something defined in sumfunction.c. I don't include this file in here because I don't need to, but I link it in when I compile, which you noticed. Let's scroll up. We saw when we compiled mysum right there, we linked in the binary from sumfunction.o. Cool, and I don't need the header file because, of course, there's the function declaration. So sharp include normally just puts in a function declaration. Here I've just put it straight in the code. And so all I need to do is link in the binary, which I do. Any guesses for what is in sumfunction.c? What code I've written in sumfunction.c? Any guesses? Yeah. Yeah, so I write int sum, int a. I write this line, and then I have open curly brace, close curly brace. What do you think I write inside those curly braces? Inside that function? Yeah. That's a really good guess. Who thinks Madhu's right? It says return a plus b. Okay, not everybody. Akshar, you do too? You sure? Okay. No. Oops. What? No, I didn't. Yeah, just kidding. You're right. All right, you're right. That's exactly what it does. It's return a plus b. That makes a lot of sense. Okay, let's go back here. We see how the header, that's the return type. Remember, we've seen that day 1, the return type of the function, but goes before the name of the function. Here I've written int. What do you think will happen if in this function I don't write int, but I write unsigned? The difference, of course, being that unsigned represents only positive integers, and int can be positive or negative. So I've changed the return type of this function. This code does not match this return type here. What do you think will happen when I compile? Should yell at me. No yelling. What about when I run the program? Let's do before 0, -3, or -1. It still works. even though I'm saying it's returning an unsigned integer, clearly it's not returning an unsigned integer. Clearly it's returning a signed integer. It's returning -1. Okay, that's weird. What about if I go in here and do that? So I've changed everything from an int to an unsigned. It can only take the unsigned integers, but do we still think it'll run? It will. That's crazy. And we pass it an clearly assigned integer. We can pass it 2 signed integers. It still works. Okay, any ideas of why it still works or what's going on? Yeah, Jeff.
Is that something to do with your optimization that you're having in the compiler?
No, we could change the optimization. It would still work. I can do that for you, but yeah. If you open the make file right here, I changed the optimization. So you can do -00. It will still work. Other thoughts? You guys all expected it to work, so why do you expect it to work? No silence. Okay. I have to wait 7 seconds because I asked a question. Okay, so the cool thing about C, and you've probably experienced this before, you might not have, this might be the first time, but as you all know, when I write something in C, it's not saved like this on the computer. It's saved as 1s and 0s. It goes from C code to assembly code. Has anybody seen assembly code before? Okay. Machine assembly code. We'll look at it in a second. It goes from C code to assembly code, and you guys know the stages of compilation. You had to memorize that for quiz 1 and then write it out on quiz 0. Most people got it wrong. I think you guys nailed it, but you guys are like the best section for quizzes, by the way, which is awesome. It won't hurt you. Don't be worried, but it's really cool. Good job. So it goes to assembly language, and then it goes to 1s and 0s. And the 1s and 0s are saved on the computer, and that's what's saved in the a.out, or in this case, the executable file. And the computer runs 1s and 0s. Right? We've learned this before. So the cool thing is this unsigned idea, the idea of types, ints, unsigned, et cetera, that's up here in the C language. Those exist. But types don't exist at the 1s and 0s. Types don't even really exist at the assembly language level. So that's something that exists in C world, but doesn't exist in computer world or processor world. That's some abstraction that the C language has included to make our lives easier. So at the end of the day, I can write many different things here, and it doesn't make a difference, because that only exists in the C world. It doesn't exist in the 1s and 0s world. And our program's executing in the 1s and 0s world. So that's the first. Okay, your mind's clearly not blown yet, but I think that's cool. Yeah, Jeff.
So if instead of doing int, you did a char.
Let's do it in a sec.
So because then you get an unsigned going from -128, 127, or 0 to 255. Right?
So char is problematic. Does anybody know why a char would be problematic and it would actually change things in the 1s and 0s world?
What's the size of char?
Size of char is 1. So unsigned is also 4 bytes. So char would screw things up. But what is 4 bytes? That's related to a char. Or that adds one additional, if you put one more character after char, char star is 4 bytes. So let's do something that's a char star. So this would probably work, but we're going to do something even crazier than this. Or in my opinion, crazier. Okay. I've now written a function that returns a pointer, and it takes a pointer and an unsigned value. We'll change this back to int so we're not making too many changes at once. And it has an array called A, indexes into the array, and returns the address of. We've seen all these operators before. What do you think this is going to do in return when I run it? What do you think it's going to do? Any guesses? What? Segfault? That's a good guess. Tom says the same thing. Any other guesses? Who thinks it's going to do the same thing? Who thinks it's going to segfault? does the same thing. I'm sorry. But, of course, we put in 1 and 2, and those are both valid, right? Let's see. We can go to the second place of an array. But what if we put, made B a negative number? That is probably a better guess for something segfaulting. It still works. Okay. This is now crazy. This is an equally valid sum function. This does the same exact thing as return A and B. Can anybody explain why this is a good sum function and why this works? What is happening here? Why is this does the exact same thing as our old sum function? Akshar, what's going on?
Because when you give an A, that's an address to a location in memory, and then when you do the ampersand, it goes to that memory address. And then when you go to B, you're kind of moving steps from that memory address, and you're returning that. So you're actually, in effect, adding A and B.
Does that, yeah.
Where's the order of operations on that return? Where did the parentheses fall? Is it returning the address of A before or after A?
It's going to index into B, or index into A, and then return the address. Okay, so did everybody understand what Akshar said and explained? Why this works? I didn't the first time somebody explained this to me. Okay, would anybody like a picture to explain this? Avi. Okay, we're going to draw a picture with no markers. That's great. Found some. Okay, so we have an array that's a series of boxes. The first one is at index 0, index 1, 2, 3, 4, ... and a typical array. And in addition to having indices, they all have memory addresses. So this can have, give this memory address 13, 14, 15, 16, 17, etc. Everybody's here so far. So A is an address. The name of an array, that's all. It's a value. A pointer is saved there. It's a pointer. It's a memory location to the start of the array. So if this were the array, A would be a value of 13. And of course, we can give A any value we want. Char star A, we can give A any memory address we want. We can give it 0. We can give it -1. -1 doesn't exist, so that's probably problematic. But you saw that it still worked. So we can give A any number we want, any memory address we want. Then int B says, OK, go this number of steps into the array. So if B equals 2 and A equals 13, we're at memory address 13, and we go 2 steps in. And so we're here. And the ampersand means return the address of this location. And the address is, of course, 15. So we get 13 plus 2, or A plus B, which is 15. The question is, though, sorry, does that clarify things for why this works?
Why would it work so you can have an array and go to a negative index?
Right, so we did negative numbers. So that's the question. Does this make sense, though, first, Avi, for you? Yeah. What? Yeah, so this would return 15. If A was 13 and B was 2, this would return 15.
So the 0 indexing doesn't become an issue, right?
No.
Because you're moving from 0.
Right, so you're moving. So if B was 0, you wouldn't move anywhere, and you just return the address of. If B was 0, that's essentially returning the address of A. Returning the address, passing in char star A and returning the address of A is just returning A, essentially. Okay. The question is, why do negative numbers work? And that's the really cool thing about this, because this should segfault, and it would segfault if we did something like this. Let's say int. So this code looks identical and should behave identically. We've essentially, x is a garbage variable, and so this should behave identically. Let's make this. Oops. In star. Wait, address of state. OK. We're already getting errors here because it's already going to be angry at me because it already knows what's coming. In particular, the second one, address of stack memory associated with the local variable. essentially, I'm not going to compile this in, and I'm going to undo what we just did. But because we're never actually accessing what's at the memory location, it's not going to segfault. We're never actually looking at what's in the second box or what's in any box of this array. We're only saying, here's the address of the thing we're looking for, and return that address. We're never actually going into the array to look at that location. And because we never touch the memory, we don't get in trouble. We don't get a segfault. If we tried to, again, touch that memory, touch what was at A or B, or A bracket B, and assuming A was 0, and if A was 0 even, that would be pretty bad because we can't go down all the way there. If A and B were both 0 and we tried to touch what was there, then we would get in trouble. But if we don't touch what's there, we just return the address, it is actually not going to segfault because it lets you perform those operations. It only gets mad at you and gets super angry when you try and touch the actual memory and return what's at that memory location. Does that make sense? That's just a crazy part of C. Okay, so we have one more of these. Okay, who thinks this is cool? More people. That's good. Okay, this is our last one. And I would like you to tell me whether or not you think this is going to do the same exact thing. Oops. I have these written down somewhere. I'm not memorizing them. Oops. Let's see, 8B, 44, 24, 08, 03, 44, 24, 04. Okay. So this is an array now, not a function. And it's array because we have square brackets, not curly braces. And it's an array of what type? Anyone? But what's the C type? They are hexadecimal numbers. What's the C type? It tells you. Right, unsigned chars. So and 2 hexadecimal numbers is 1 byte. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. It's an array of 9 bytes. Okay. You probably already know the answer to this question, but what do you think will happen when I run this? I say, again, in mysum.c, I'm expecting a function that takes 2 integers. And I'm instead saying that sum is an array of characters. What is going to happen when I run /mysum and make? Well, first, most of you would probably agree that make, oh, no, just kidding. What did I do wrong? Uh-oh. That should be curly braces. That's how you initialize an array. My bad. Okay. So we already saw before that types are an C-level abstraction, not a computer-level abstraction. So most of you probably expected it to make, or were assuming that it would make. But what happens when I run /mysum? What's going to happen? Any guesses? It's going to print out a word. What word? Any other guesses? Okay, print out a phrase. You can have any phrase. That will be your side. Anybody who has a different guess? Anna, what's your guess? One letter. 9. Well, I'm going to run it. It does the same exact thing. It adds 2 numbers together. Well, let's pass it to arguments. It doesn't take arguments, so I don't know where it could possibly get these arguments. But let's pass it 100 and 0, and it adds 100 and 0. That's insane. I think so. -4. That works too. You can do anything you want. This is an equally valid sum function. This is a sum function. But no, you're saying it's an array of bytes. So what is going on here? So again, let's go back to this idea that we said at the very beginning. You go from C-level code to assembly language to ones and zeros. This is hexadecimal, but this is really just a lot of ones and zeros. This is 72 ones and zeros, right? 72 ones and zeros, 9 bytes. Each byte has 8 bits. Each bit is a 1 or a 0. So 72 ones or zeros, I've just written them like this rather than writing it out as a lot of ones and zeros. But this will go from C-level language to assembly language to code, and this will print out in code somewhere these 72 ones and zeros that I've written here. So somewhere in that, let's go here. Somewhere in my sum, the program, there are these 72 ones and zeros that I've written and told it to write. Now, any guesses for what those 72 ones and zeros mean? Probably the same thing as return A plus B. Let's verify that. Let's figure out how I did this. So if you go back here, I tell you to run this command, objump-s sumfunction.o. Let's go run it. Objump, basically it can give me whatever I want to see. It can give me the assembly language. It can give me the ones and zeros. It has a ton of flags. This is the one we're going to use for now. As you see in the slides, -S says intersperse source code, the lines from C with the assembly code and with the ones and zeros. And we're going to run it on sumfunction.o because it'll be easier to see. Again, you're right. But I'm going to actually clear it for a second. I'm first going to open just sumfunction.o. Classic. Okay. That is a hard word, though. You'd be surprised. Okay. So this is sumfunction.o. I couldn't even tell you, there's a lot of zeros, clearly a lot of zeros, and there's some other stuff that's not zeros, but mostly zeros. Looks like there's some ones. So clearly this is hard to read. That's the binary language. Let's now open it. What? What am I doing wrong? Did I spell it correctly? Okay, this is awkward. Okay. I need 1 second to figure out what I'm doing wrong. That's one error. That's weird. Okay. Oh. That's why. I'm going to go back to our initial one. So we can look at the object code of this, because there's not really going to be anything when we just put the ones and zeros in. B. There we go. Okay, so everybody can see this. This function, as I said, put out the C lines, source code lines, with some assembly instructions. Here is our source code line. Here's one. Here's another. Here is the assembly instruction. That's what they look like. Assembly instructions, you can learn more of these if you take other CS classes, but they're generally an instruction, and then a source, and a destination. And then over here is the binary code that corresponds to that assembly instruction. So as you can see, this sum function, at the end of the day, is 3 assembly instructions, only 3. One move, this MOV stands for a move, add stands for add, and return, RET stands for return. So one move, one add, one return, and these over here are the zeros and ones that correspond to that code. So those zeros and ones, if you know those, you can just put those straight in, and then it'll do the same exact thing. Because at the end of the day, all you're executing is a long series of zeros and ones, and that's what your code really is. And the reason, let's look at one thing. Did I have the makefile open? So we went back to -00 up here. Sorry, capital O. Capital O0, not 00. And we did make. It would still work, all work the same. But now you notice that there are a lot more assembly instructions. That's because, again, I asked the compiler not to do any optimization. So I could still take all of these zeros and ones and throw them in, and that would work. I just did the optimizations because it's a bit easier then to write that array. But this would work just as well. OK, we're going to do one final thing, because I think this is the coolest part. Even though everybody's clearly already blown and speechless. Our minds are blown. Let's go to... So these are from a different CS class, which is super interesting, that I have taken, CS61. I highly encourage you to take it. But the cool part about this fact that things are just zeros and ones are that everything is zeros and ones. So you can take a file that has the correct zeros and ones you want somewhere in it and use that section of zeros and ones as a sum function. What do I mean by that? I mean, you can take an image file that has the correct series of zeros and ones that prints something out to an image, and one program might interpret it as an image, but you can interpret it if you want as a sum function. So if we wanted to open, for example, this image, let's go. Hello Kitty. Wonderful little image. In here, there is that string of zeros and ones. Those 72 zeros and ones exist in this image. So what I can do then is write, and I have to remember where they are. I'll find that in a second, but we can do let me find out where they are. One sec. Let's do... Thanks. So if we execute this program, which instead reads in a file, then goes to this index in the file, and then, again, just like MySum, takes two numbers, we can add numbers exactly the same as we were doing before, which goes to show you how the fact that at the end of the day, all these things are zeros and ones, and it's just how you choose to interpret them. And if you actually look at this image, let's zoom in a bit. Can everybody see? You'll notice right here, there's some weird smudge. Let's go. This is the original image. You'll notice here there's no smudge. That is the code for the sum function, is that little smudge right there. And actually, again, if you learn more about this, you'll realize that this Hello Kitty, which has even a bigger smudge, has code that can take over a computer if it's not protected appropriately. So you can actually run this. I'm not going to run it right now, but but you can run this Hello Kitty image, and it can take over your computer. So does anybody have any? That's all for the demo. Does anybody have any questions, comments, concerns? I think this stuff is fascinating. It inspired me to learn more. I highly recommend, if you're interested at all in CS, talk to me, even though I'm a social studies concentrator. I'm CS secondary, so I still know a bit. But I certainly know what classes you should take. I think it's all really interesting, and I encourage you certainly to learn more if you're interested. OK, I have one final thing. Any questions? I didn't pause to wait if anybody had any questions about that. All right, is anybody becoming a CS or going to be a CS concentrator or thinking about it? 1, 2, 3, 4. 1, only one. Anna's is the only hand that's raised. Authoritatively, like with, yeah, there we go. Okay, that's cool. Assam, what are you going to do? Oh, Constantine? Whoa, that's fast. You had a bad experience in CS50? You, what are you going to do? Kurt? Econ or CS. Tom? Stat. Oh, okay. What are you? Yeah. Stat. Oh, here you go. Time to talk to Alden. Emily, what are you? Are you in this section? Okay, that's Emily. She's my friend. Clearly not that good of a friend. Because she gives me a hard time. You could be nicer to me in front of everyone. My student. Oh, really? Uh-oh. Okay, you're amazing. I love you so much. Oh, boy. Anyway. Okay, so last night, like everything, I'm sure everybody's feeling like really stressed right now. If you're, I don't know, are freshmen, are you guys feeling stressed? I'm feeling stressed. It was like, you go home for Thanksgiving, you're like, I'm going to do all these things. And then, yeah, and you come back. Jeff, you don't feel that way?
I just don't want to deal with it.
Okay, great. So I come back and I haven't done anything, and it's all super stressful, and I'm concerned, genuinely concerned about whether or not I'm going to finish everything I have to. But last night I was not stressed. I was just a little bit sad, so I wrote in my journal about what I was sad about, and I was sad about this section and this class coming to an end. So I was just going to read for you guys a little snippet of my journal from last night. Can I get some napkins, some tissues from Tom? No, I'm not going to cry. I don't cry. Not that you can't cry, just don't cry. I don't even know if my tear glands worked. Tear ducts. I haven't cried in a long time. Okay, thanks. Okay, there's a little preface. There's some other parts of my journal entry, because I try and journal every night before I go to bed. I highly recommend journaling. It helps you process things and also be very appreciative of your day. And it makes it a lot easier to look back on your day and realize that there were a lot of good things that happened, even if you feel really stressed at night or really upset or really sad or tired. Oh my God. Okay. So, I don't even know if it's written that well because I didn't proofread it, but we'll read it. I usually don't read my journal, obviously. Tomorrow, I'll also teach my final CS50 section of the year. It's crazy how fast time flies. Yet I'm struck by just how different my experience teaching this year was than when I was a sophomore. For starters, I definitely know the material better, but don't tell my first cohort of students that. More importantly, however, I realize that the joy that comes from standing up in front of a room of what starts out as strangers but ends up as, at least, Facebook friends, is not a first-year fluke. Rather, it's from knowing that you're in some small way helping talented, thoughtful, delightful, and passionate people learn a bit more about computer science. You're shifting that light bulb just a bit in its socket so that it's able to shine brighter than you or they could have imagined at semester's start. You're helping turn those frowns upside down and asking questions that provide support but still allows students to stand up on their own. It's certainly not an exaggeration to say that this section is my favorite part of the week, or even that I hesitate to say, that's all, at 5:30 p.m. each week, knowing that it'll be way too long until we meet again. Yet I'm incredibly thankful to everyone who's given me this opportunity to give back to others. To David for his patience and trust, to the film and production crew for making me look somewhat respectable, and most importantly, to my students, without whom I'd have no reason to spend 10 hours figuring out the best way to draw pointers or lay out a table of dolphins via JavaScript. As always, it's been a blessing. So with that, thank you guys. I'll see you all at the CS50 Fair and the hackathon if you're there. And if you have questions, I'll stick around until there are no more. But thank you guys for a wonderful year. I might cry.